Hey everybody, this is Larry. This is me going Cube 4 of the weekly contest 261, smallest K-length subsequence with occurrences of a letter. So this one is kind of tricky, but to be frank, it is, I wouldn't say it's standard, but it uses a technique that comes up from time to time in terms of competitive programming. On interviews, it's probably a little bit too hard, so I would probably focus on maybe easier versions of this problem first at least, but I wouldn't even consider this technique maybe in scope, at least not directly. Like maybe you could use this technique to solve other problems, but yeah. And the way that I would solve this problem is by, would I call it greedy? I don't know if I would call it greedy, but let's call it greedy. Just greedy, right? It's basically, we know that we have to have K letters. We know, that we have to have repetition number of a letter. So then these are the constraints that we have, right? And we have to construct this from this subsequence, right? So then the greedy part of this is just asking yourself, okay, one character at a time, can I put an A here? Can I put a B here? Can I put a C here? Can I put a D here as the first character? Okay, let me rephrase that. Can I put an A here? And can you hit the like button? Can you hit the subscribe button? Can you join me on Discord and chat about this problem and other Leetcode contest problems, especially right after the contest. But yeah, what I would say is, yeah, so your question is one character at a time, and we know that we need to have length K, so these are the constraints that we have, right? So for the first character, we ask, can it be an A? Yes. If yes, then you just make it an A. Can it be, and then as second character, can it be an A? Can it be a B? No. Can it be a C? No. Okay, and then so forth, right? So that's basically the general idea. That's the general concept, and this is a technique that comes up from time to time, like I said. And then the question is, how do you answer the can it be an A part, right? Well, I think that's the trickier part, but not that tricky. It's just implementation at that point. And then now you just have to ask yourself, okay, if I put an A here, can these constraints still be satisfied, right? And that's basically the idea I have. Let's see if I have a better example to kind of go through one with you. But yeah, let's say we have this one then. Yeah, let's just put it here so I have a better visualization. But yeah, let's say we have this one. So we try an A. Well, there's no A in this word, so let's just, we don't try A at all. And then we try the first character is B. Nope. C. Well, there is a C here. Can the first character be C? Well, no, because if we choose C, that means that we have to use only the suffix of C, and that means that, well, there's only one Y left, so that means that this is not possible. Okay, right? I hope that makes sense. What if the first character is a D? Well, same idea, there is a D, but that means that there's not enough characters to, well, the multiple things that it violates, right? One is that there are not enough characters to fit the K equals 4, and then the other one is that, you don't have enough Y's to fit it, right? So D is not true. Okay, what about Y? Okay. If we choose Y, then we greedily will choose the leftmost Y because that gives us more choices in the future. So greedily, you always choose the earliest categorization. Like for example, if there are multiple C's, you would also choose the earliest C because that just gives you more option, right? Like even if there are multiple things in between, right? So yeah, so in this case, we choose Y, and then now, what happens after we choose this Y? Well, we know that we have enough characters to the suffix to fit K. We know that we have enough letters Y left, so that's basically it, right? So okay, so now let's say we choose the first letter to be Y. So then that means that we eliminate everything to the left of it because, well, there's no need. Because, well, you can't go backwards because there's a subsequence, right? Going from left to right. So let's subtract this. K, now we only need K equals to 3. Well, the letter is the same, but repetition is now 1 because, well, the letter is the same. So then now we ask ourselves, can the first character be an A? Well, there's no A, there's no B. Can it be a C? Can it be a C? Well, the answer is okay. The suffix, we can definitely have a K equals 3 left, and we can have 1 E in the suffix. So let's take this as a C. Yeah. And then now we try it again. We have to choose this to 2. We don't change the repetition because this is not a E, right? So then now we go A, B, C, D. Can it be a D? Actually, yes, right? Because it has 1 E in the suffix, and also it has at least 2 characters. So then this could be a D, and get rid of the stuff in the left, change this to 1. And then of course the last character is a E, and that's all you have. That's basically the idea in English. Of course, implementation is hard, and that's where you have to put all these things together. Okay, so I'll go over my solution with that idea in mind. Hopefully that's a good explanation. But basically I have a deck that gives me the index of every character in order, right? So now C contains the indexes of every character, every letter, maybe that's a better word. Every letter in sorted order, right? Because we're just going from left to right. So yeah. So this gives us a list of the characters. For example, if this is Leetcode, the word is Leetcode, then the letter E would have 1, 2, and I guess this is 7. So yeah, right? And why I do this, we'll see in a second. And we have a deck so that we can pop off from the left. So then here, yeah, so this is just for answer, and this is where the last character was. So it just keeps track of where the last character was. And then now we do what we said. So we have to construct a string of length k. So this is why this loop is here. And then now we do one character at a time. We start with A, B, C. We start with A, and then B, and then C, and then so forth. If the constraints are met, we have a break so that we go to the next I. But yeah, and we're skipping ahead a little bit. So we have this loop here. What does this loop do, right? This loop basically is saying that we want to remove from the beginning of all the characters that we already removed, right? By that I mean, for example, if we choose a C, then later on we want to remove all these characters, so we remove the beginning of the deck to kind of make sure that that happens. Yeah. And then here, this part is it's a lot of the things that we asked, but in a lot of code, right? So basically, we ask, okay, for this, I'm gonna say the word, I'm gonna say the character A, pretending using A as an example, right? So okay, is there any more A? If the index of the A is after the last character, then we just move it because we don't consider it anymore. Okay. And then now after removing all of the ones that are no longer, in the suffix, then we ask, are there any A's left, right? That seems pretty straightforward. And then here is what we said earlier. This is basically, if we use this index, this is the number of characters in the suffix, right? So yeah, because we always use the first index. So this is the number of the characters left if we use this. And this is the number of characters we need to have left. So basically, this is saying if the suffix is long enough to use this letter, then we go on to more conditions, right? Yeah. And then here we go, okay, if we use this character, are there enough of the good letter, the letter left, right? And that's basically what this logic does. This logic goes, okay, let me binary search on this index that we just, thingy. And how many are there left? Well, it's just the number of the suffix that are left after. Because if we use this character at this index, then we would have to remove everything to the left of this on the suffix. So then this is the number of characters left of the good characters that we care about. And then now we ask, is there enough? If the letter that we're parsing now, if the letter that we're parsing now is equal, then this is just counting the number of repetition and whether this can be fulfilled. And if this condition can be fulfilled, that means the number of letters that are left have enough repetition, and if there are just letters that are left in general, then yeah. Oh, so this is basically the suffix has to be greater than repetition, otherwise you just don't have enough letters left. Even if you have enough ye's, for example, this is just saying for the Leetcode case, for example 2, this is saying, are there enough ye's left if we put it here? Okay, and this is good if this is good. What this is saying is, if we use these characters, are there enough characters left to have ye's, right? For example, so this is the case that I failed on, and I had to add this case. If you have A, B, 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 and you're trying to make sure that you have enough, let's say you have forced to have 5 B's. If you go A once, then you're not, and K is you go to 5. If you go A here, you will have enough B's in the suffix, but you won't have enough time to put in, because even if you put the rest as 4 B's, you won't have 5 B's, right? So that's basically, that's what this conditional is doing. And yeah. And then here, once we do it, we put it as the answer, we pop left, we pop it off the index, we append the answer, the character is the answer. If the character is a good character, we remove one of the repetition needed, and at the very end, we just return it to a string. And that's pretty much the idea. Yeah. So what is the complexity for this one, right? So the complexity for this one is actually just linear time, linear space. Even though this looks, linear times alpha, right? So alpha is the number of characters in the alphabet. So in this case, it's alpha times, in this case, alpha would be 26. And yeah. And in this case, it'll be 26 times n, which is alpha times n, or O of n, or whatever you want to call it. Yeah, and that's just because, you know, the outer loop, actually, is it n? Yeah, I guess it's still n, even though this is k, because we can pop it off. There are a lot of while loops in here, or there's this while loop. The reason why this is linear time in total is because you can think about each index gets put into this thing once, and then every index can at most be popped once. So therefore, it takes linear space and linear time for this one. Sorry, I lied for this one because of this binary search. So this is actually O of alpha times n log n, because this can be searched at most n times, and each one is log n. So let me write it down. Time is equal to O of alpha times A for alpha times n log n, and space is just O of O of n, right? Because even though there's at most 26 characters, each letter of S will have at most one index, so it's just O of n, right? Yeah. And that's all I have for this one. Let me know what you think. It's a tough one for sure, but I found this one better or easier than Q3. I don't know, you agree? Let me know what you think. But this one is more standard than Q3. I think that's why I consider it quote unquote easier. But yeah, you could watch me solve it live during the contest next. Oh well. Okay. So yeah, that was a waste of time, but yeah, I don't know. That was a mess. Okay. You're given a string S and an integer K. I mean, so I'm really behind, and there's only 9. Well, actually, a lot of people got it, so maybe that's not bad. And a lot of people didn't get C. Q3. Okay. Lexicographically smallest subsequence of S of length K. That's the letter that has appeared at least repetition times. Okay. So we have the letter Y that repeats 3 times. Okay. Okay. repetition, so 2 ye's. How long do people do to get it? People seem to get this one pretty quickly. We took 8 minutes and a wrong answer. Okay, so we have to do something smarter than brute force, I imagine. But because n choose k is going to be long. And that we yeah, and I actually had to write that. I knew that approach, but I just couldn't prove it. Okay, now I focus on this problem. Okay, so here. How do we want to think about this? What is the right approach? So here we can use sliding window and then choose the smallest thingy. Is that reasonable? Because basically the repetition of 2, we use sliding window, so we have these 2, and then that means that, what does that mean, right? That means that we can take any smaller letters after it. So then this would be EECE, maybe, if we did the sliding window approach with kind of just like lexicographically smallest. And then if we slide to the EE, then now what? Well, we take the smallest that's inside and can we do that in a very fast way? Because basically now we want to do something like ETCODE, and then now we want to do, how do we get 2 letters out of these usage and everything in the suffix as well, though that's not noted. But basically we want to get, okay, maybe another way of putting it is taking the suffix and then, okay, I mean greedy is probably enough. No, because then it gets n squared if we do something really dumb. So you go, okay, can the second letter be A, right? Yeah, I think they let you notice that is E, but you can actually have an A that's early on that contains it, and that would be better. So then the question is, I think it's just character by character of, can we pick an A on the first character? The answer is yes, then yeah, I think that should be good enough. I don't know how to code it quite. We're at 45 minutes, but I think that should be a good enough solution though. Okay, so then now we have, let's see, yeah, for I, X in S, in enumerate S, let's go at C of X dot append I, and C of course is a default dict of a list. Okay, and then now we constructed one by one. Yeah, okay, so then answer is equal to this. We return to the dot join answer, and now we go for I in range of K, yeah, K, so one character at a time. We go, okay, can the first character be 26 or 20, be A, right? And then now and we also added maybe the last is equal to -1 or something like that. The last character used. Oh, then here we ask, okay, for a character. Actually, I'm just see then. Whatever, for t in range of 26. Okay, so what is that Python ASCII lowercase thing? I actually don't. Okay. Okay, let's do that instead then. Is that the right one? String dot. Okay. That should be right? Okay. Okay. So we can use a if we can use this character if there's if c of t if length of this is greater than 0. Actually, what we should do is while c of t is less than last. We should actually make this attack c dot t dot pop left. If length of t is greater than 0 and c of t of 0, if we take this, what does that mean? This is the index, so we have n minus whatever characters left, maybe off by 1, but this will get us a good start. If this gives us more letters than k minus I, then I think we're good. Then yeah, then last is equal to we break and answer dot append t. Oh, I have this is mostly okay, but well, this is just also wrong, but we have to force the ye times. Maybe I didn't think about that way. How do we enforce this? Dong dong dong. Dong dong. Okay. We enforce this by asking, is there still more yeast left of this letter? Okay. Let's play around with that in a second. We have 45 minutes left. This is a tricky one to get right. But I don't even know how this happened, so maybe I need to fix that first. Because it should give us, oh, why is that wrong too? Did I not update last? Oh, I just didn't update it. Oh, I have a typo, so maybe that should be okay. Okay, so now this is the right answer ish. Well, what? Oh yeah, this is the right answer ish, in that this is if it doesn't have the constraints of the multiple letters. So then now we have to do a binary search on this, meaning if we take this, then how many ye's are there left? Yeah. Okay. And maybe is it bicycle left? Well, it doesn't matter because C of letter. If we take the last, then how many do we have left? Right. So this is the index of the thing. Okay, let's put it here. L left for letters left. So this is the index which we insert. So that means that length of C of letter minus left is yeah, let's just say this is yeah, can left maybe. This is always awkward. Yeah, okay. If C left is greater than repetition, then we're good. Then we do this thing. Yeah, okay. And then here we also have to add it in a thing that I just forgot or didn't consider. Letter is equal to T, then repetition, because then we already used it once. Okay. Okay. I mean, we're somewhere. Not where we like, but somewhere. Okay. Okay, let's print this out real quick. So last left index C of letter. Okay. So in here we have, what am I printing here? So we have the last, okay. I'm not bisecting on this. I'm bisecting on C dot T of 0. That's why. Okay, E, C, D, C, E. That looks good. Yeah, I mean, I think any debugging I do will probably take longer than 5 minutes. So I'm going to YOLO and hope for the best. Probably wrong answer though. This judging is taking so long. Okay. Yeah, I mean, I definitely miss, like I said, there might be some off by one here, but I think we're in a good place. We have 40 minutes left. I wish I didn't, you know, get wrong answers, but that's fine. Okay, so A. So A's we have, or B's we have 3, 4, and 5. So we try putting an A. Let's see, what am I doing? So we try putting an A, and it looks like we have enough letters, but why? Because it thinks it has 3 repetitions left. Okay, so my condition isn't quite right. So oh yeah, so it tries to put the second A, but we need the second A. So we need one more condition, which is that if we put this here, we don't use up a repetition. So okay, if letter is not T, then we do this thing. Because if his letter is T, then I think we're good anyway. That's where the bisect left is good, but I think here we said we have enough B's for the repetition, but we did not force to use them. How do I force to use it here? I guess if so we cannot use A the second time, because using it means that yeah, okay, let's see. If using it means that so this is the fewer than whatever part. So the left is equal to repetition, but the other thing is if k minus I, which is the number of characters left, is greater than repetition, and only if they're not the same. Okay. And letter is not T. Okay, see if that's good. Nope. So the letters left oh, because okay, so I want this to only happen if letters is not okay. That's why. So if letter is equal to T, okay, condition is equal to k minus I is greater than repetition. I forgot. Oh, I didn't do an if statement quite well. I mean, this is just way to or this thing let's see. Okay, so are we Gucci here? Let's give it submit. Probably should have took a second thought look at it first though, to be honest, because I think I rushed this one a little bit, but maybe. Okay, cool. Yeah, I mean, I think I like this problem. Cute videos are yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and other contest problems. Stay cool, stay healthy, to good mental health. Have a great rest of the weekend, and I will see you later. Bye bye.